All right, so let's start for today's webinar. All right, so good afternoon, everyone. Very welcome to join our IEEE Vehicular Technology Society Western Australia chapter, the first Women in Engineering event. So today, we are very honored to invite one of the excellent researchers in the vehicular technology as well as the intelligent transportation systems, and Dr. Chao Huang, so who will give us the talk entitled Autonomous and Interactive Mobile Systems. So before Dr. Huang give us the talk, I would like to give a very brief introduction about the speaker. So Dr. Chao Huang is a senior lecturer at the School of Electrical and Mechanical Engineering at Adelaide University. Prior to joining Adelaide University, she was a research assistant professor at the Hong Kong Polytechnic University. She earned her PhD from University of Wollongong, Australia in 2018, and holds a bachelor degree in automation from China University of Petroleum, Beijing. Dr. Huang has authored or co-authored over 100 papers in conferences, book chapters, and journals, with many of them published in top tier and highly reputational journals, including across diverse fields, including mechanical engineering, civil engineering, electrical engineering, etc. And currently, Dr. Huang serves as an associate editor for several prestigious journals, engineering, applications of artificial intelligence, IEEE transactions on intelligent vehicles, transportation, electrification, IEEE Women Engineering magazine, and as well as many other reputational journals. So Dr. Huang is actually involved in organizing and chairing in international conferences and academic events. She has served as the program chair for prominent conferences such as CEE VTS 2024, IETSC 2024, and CVCI 2024, demonstrating her leadership in shaping the direction of academic disclosure and research agendas in electric vehicles and intelligent transportation systems. So now let's warmly welcome Dr. Huang to give us the talk. Thank you.
Thank you. Thank you for the introduction. Let me share my screen. So can anyone see my screen?
Yes, all good. Thank you.
Thank you. So before I begin, I would like to thank Dr. Zhang and Professor Wang for their kind invitation and for giving me this opportunity to let me introduce my work in this IEEE VTS WA chapter. As Professor Wang mentioned, I completed my PhD at University of Wollongong, and after that, I have been worked in Japan, Singapore, Hong Kong. And last July, I just joined Adelaide University as a senior lecturer. So this is my research focus. My research area is mobile robots. We know that the mobile robot has a strong mobility capability to respond to the changes in the environment and can independently navigate, plan, and control its action. So based on the working environment, it can be grounded into the different groups, like ground vehicle for passenger delivery, indoor robot for customer service, and area UAV for parcel delivery, traffic surveillance, and so on. So my main research focus on these first three groups: ground vehicle, indoor robots, and UAV. So if we further break them down, we can obtain this figure. It actually contains 10 research topics. So I just find that due to the time limitations, I cannot introduce all of them. I may just first briefly introduce the idea behind these 10 topics and then select some representative topic and provide the details. Okay, I may spend more time on the intelligent vehicle systems. I believe it aligns with the topics and focus in this society. So first thing is the single UAV control and application. So the one fundamental research question is called waypoint life. So we want the UAV to quickly go through a series of waypoints without collisions and with a minimal checking errors. To address this problem, we divided a sequence convex programming framework for agile flight. And this trajectory planning problem can be formalized as a time optimization problem subject to a series of safety constraints. And since this original problem is highly non-convex, we actually transfer it to a sequence of convex optimization problems through successive convexification and discretization. So this allows us to have a high efficient computation of high quality trajectory. And the last one is called landing. So we believe that in the future transportation system, we're going to have some big UAV. We call it UAV carrier. And as you know, due to the battery limitations, the small UAV cannot fly for a long time at a long distance. We would like the small UAV to land on the big UAV, the UAV carrier, for recharging or for maintenance. So how to make the UAV successfully and safely land on the moving area platform is our second research topic. And after we actually can enable the UAV to secure and accurately land on the moving platform, it opens up possibility for various applications, including parcel delivery, surveillance, secure operation. So we just try to leverage the combination of UAV and public transportation train for parcel delivery. So in the third case, UAV has the ability to safely take off from the train and rapidly fly to deliver the parcels and then return to land on the train for recharging. The second thing is the multi-UAV and control and application. In this direction, we mainly study how to use a group of UAV to monitor the traffic. Maybe in the normal case, we would like the UAV to monitor the vehicle as many as possible. But when an accident occurs, we hope that UAV can gather and collect the data as much as possible. And in the fifth topic is also about parcel delivery. But in this case, we're going to have multiple UAV, multiple customers, and we will have well-developed charging stations. But in this case, we need to decide at what time and which charging station the UAV need to land and for charging. And if multi-UAVs land on the same charging station, we also need to determine the charging sequence so that the final objective is to deliver the parcels to all of the customers before the deadline and with a minimal overall energy consumption. And then last one is about data collection. And in this case, we actually have a team of UAV and vehicles. We believe that a team of UAV and vehicles is a promising tool to improve the communication for tasks like load balancing or a cost-efficient routine. So we find that in the existing method, they always assume that they always focus on the security and communication aspects, such as bandwidth allocation. But in our case, however, from a control perspective, we design UAV navigation paths to efficiently collect the data from the vehicle. And the third theme is about ground vehicles. It can be divided into human-centered cooperative driving and fully autonomous driving. So we know due to the safety issue, privacy issues, sometimes we still need the drivers in the loop of the controls, vehicle control. So in this case, we call it human-centered cooperative driving. We still need the driver to monitor the vehicles, but we can provide some assistance if there is a need. And regarding the autonomous driving, we focus on the decision-making part because we believe that decision-making part is quite important. It can determine the vehicle steps. So in this case, we actually design a series of human-guided reinforcement learning algorithms. I will introduce it later. Last one is the indoor robot systems. So in my view, we think that indoor robot system has a similar structure with the vehicle systems. They also need to do the perception, decision-making, navigation, and control. So in this part, one of the contributions that we involve the human voice as an input. So we can let a small robot to talk with the vehicle. Based on this interaction, the robot can do like further navigate and control. Okay, so as I said, that due to the time limitations, I will skip this part, autonomous indoor robot system, and just quickly go through this part and then pay attention to this intelligent vehicle systems. So before we talk about the technical details, let me just briefly introduce the research background of UAV. So the UAV is commonly known as a drone, and it is an aircraft without any human pilot, crew, or passengers on board. So based on the Hong Kong regulation, UAV can categorize into macro, mini, and small size according to their weight. And yeah, currently my UAVs are all mini-sized UAV. And I also checked Australia's policy and find that under Australia CASA classification framework, my UAV can be categorized as a very small size UAV. And according to the wing type, UAV can be categorized into rotary wing and fixed wing. The rotary wing is more suitable for close inspection, and fixed wing is ideal for long-distance flight. And based on the number of wing, UAV can be clarified as four types. Most widely used in my laboratory are quadcopter, the second one, with 4 wings. And we know that UAV can be utilized in various application scenarios, including but not limited to forest fire monitoring, river monitoring, and healthcare, medicine parcel delivery, photograph, or climate research. And from the control perspective, for the single UAV, the control objective may include following a desired path or minimizing the flight time. Common control algorithms involve MPC, sliding mode control, some control challenges. It encompasses the handling systems disturbance, consider battery limitations, testing scenario including the simulation environment, indoor and outdoor setting. And unlike the individual UAV control, multi-UAV research requires additional considerations such as anti-collision measures and communication interference management among the multi-UAVs. So I need to skip the background of the first research topic, then we can just quickly have a look at on the demos. So this is our indoor laboratory. It's situated on the basement floor, covering an area of 8 meter, multiple 6 meter, multiple 4 meters. We have a Vicon system. It can accurately capture the position of the UAV. Okay, and we have different size of UAV. And in this research, we just use this blue UAV with a diagonal size here. We also have a big UAV. It's called UAV carry. So later you're gonna see a video shows that how we land a small UAV on this big UAV. Okay, and this diagram on the left side, it shows that the testing framework. So you see that input signals are a series of waypoints. And then we design our trajectory planning, and output is the angular velocity and thrust signals, and they are then fed into the flight controller and control the motions of the small UAV. And the Vicon system is used to capture the states of the UAV and then put it back to the trajectory planner. So here is a demo. It shows that the UAV can successfully go through a series of waypoints. So here we actually have 1, 2, 3, 4, 7, 6, 7, 4, 5, 6, 7, 7 waypoints, and we have the computation time is quite small. So you also find that to quickly and accurately go through this waypoint, the small UAV actually conduct a series of aggressive maneuvers, including rolling, diving, and pitching afterwards. Next one is about the landing. As I mentioned, we interested in how to land a small UAV on a moving aerial platform. We find that existing methods may only focus on landing on the large board, moving ground robot, and moving ground vehicle or terrain, but we focus on landing on aerial vehicle career. We believe it is more challenging because it involves lots of uncertainties. And here are our designed algorithms. I don't want to provide the details. So if you look at this figure, it shows that how we actually developed this landing trajectory. We actually divided the entire landing trajectory into two segments. Okay. The first part ensures that UAV safely reaches above the carry platform, while the second part involved UAV descending within a landing core until it lands on the carry. Okay, and this shows our algorithm pipeline. We actually developed a trajectory based on a simple 3-degree of freedom model. But after that, we adopted sequence convex programming and to make sure that the final trajectory can successfully satisfy the 4-degree of freedom model. So here is a demo. We have 4 GIF. The top 2 GIF shows that the aerial platform is stationary and the small UAV just need to find the location of this big UAV and land on the top of the big UAV. And this bottom 2 cases, it shows that the UAV carry is moving. On the left, it shows that they are meeting in the same direction. And in the right side, it shows that they meet in the different direction. Okay. Well, yeah. So when the UAV can rapidly fly and land on the dynamic platform, we consider leveraging the UAV in conjunction with stations or trains to extend their flight range and facilities the tasks such as parcel delivery. So we have 2 application cases. First one, we consider the case that we have a number of charging stations. Okay, we have a depot, we have a customer here, and we want a small UAV to deliver the parcel from the depot to the customer. But as we know, due to the battery limitations, the small UAV cannot fly for a long time. So they has to, during the flight, the UAV has to land on one or several charging stations for recharging or maintenance. So in this case, we need to determine, okay, when and which charging station we need to select, and when the UAV has to land on the charging station, and to what percentage to charge the battery, and what if some charging stations may be unavailable. So how to solve this problem? We propose a graph construction method to formulate the problem and adopt a graph searching algorithm to plan the path. And in this case, we actually consider a public transportation system. We want to use the train to help us recharge the UAV and extend the flight of the UAV. So assume that we have time slot of a train or of several train, and we need to determine during this flight from depot to the customer on which train at what time the UAV need to land on the top of the train for recharging, and at which location the UAV needs to take off from the train and fly to the customer. As we know, the timetabling actually has lots of uncertainties. So we actually formulate it as an optimization problem with the objective of maximizing the probability of arriving at the destination within a given time. Okay, we formulate it as an optimization problem with the objective of maximizing the probability of arriving at the destination within a given time. So following the concept of stochastic domain, we developed a label setting algorithm to find this path from the depot to the customer. Okay. So I didn't provide the details here. If you are interested in, you can refer these two publications. Okay, yeah, summary. In the single UAV control and application, we actually focus on control planning and scheduling, and they can use it for extreme sports farming, inspection, parcel delivery, search and rescue. That is the travel surveillance. As I mentioned, that it used to monitor the travel. I will skip the technical part, but if you look at this chip, you're going to find that at very beginning, it is a normal case. The UAV just needs to go around and to collect to wheel the vehicles as many as possible. But somehow we find there's a traffic jam occurs. Just wait for a second. Yeah, here. And then the UAV need to change their like operation mode. They has to gather together and goes to the accident location and collect the data as much as possible. So we actually design mechanisms to like identify the different operation mode of the UAVs. Okay. Next one is also about parcel delivery, but this time we have multiple UAV and have multiple customers. So we have one depot, we have multiple UAV, like the red one, purple one, green one, blue one, and we have different customers. So in this case, we have to identify the flight trajectory for each UAV and compared to the single UAV, the challenging thing is that we need to consider the anti-collision. For example, if two UAV land on the same charging station, who will be the first one to charge the battery? Okay, and the objective also will be a little bit different because we need to consider the overall thing. So the objective will be the overall energy consumption, the average flight time, and yeah, so we actually you design and enhance the backtrack searching algorithm to make sure that the overall flight time, energy consumption, and the other important components can meet the requirements. So we actually also use the Hong Kong app to assume that we have a series of charging stations in this area. Well, next one is a collaboration work with Professor Andrew Sapkin in the UNSW. We assume that we have a group of UAV and vehicles. Okay, they are partners. And in the future, UAV and vehicle can communicate with each other and can collect the data and transfer the data through each other. Okay, so in the existing method, we find that they always have a very strong assumption that they assume that UAV can always communicate with the vehicle. It may happen like in the city area or urban area, but if we consider like a mountain road, because of the trees, sometimes UAV cannot communicate with the vehicles. So this strong assumption is not realistic. And in our algorithms, we release this assumption. So we consider the constraint, this called line of sight constraint in our optimization problem. The objective is to let the UAV transmit as much data as possible during the flight. Also, at the same time, we minimize the energy consumption and transit power. So in this case, we also want to guarantee that UAV cannot connect with the other UAVs. So we solve this problem. So we also provide analytical proof to prove that our algorithm can always provide an optimal solution. So if you see this GIF, you'll find that we have like two vehicles. These vehicles drive on the mountain road, and we have three UAVs. And during this flight and during this driving, the UAVs continues transmit the data to the vehicles, but they have to switch their partners because due to this line of sight constraint. So you're going to find that at the very beginning, the UAV one flies towards the vehicles, but at a certain time, the UAV1 stops and the UAV3 start sending the data to the app, to the vehicles. So if you see this table, it can show it very clearly. So in this case, we consider that 4 vehicles and 3 UAV. So it means that the number of vehicles is larger than the number of UAV. If you see this, look at this first row, you're going to find that at very beginning, the UAV2 transmit the data to the vehicle 1. But during this time period, the UAV2 switch its partner, is start sending the data to the vehicle 3. Because due to our optimization algorithms, we find that at this moment, UAV2 cannot communicate with the vehicle 1 due to the line of sight constraint. So to achieve a minimal data, we have to switch the partner. That's kind of our contribution in this case. Okay, so next topic is about intelligent vehicle. Let's first talk about the human-machine cooperative driving. So this is the motivation of the human-machine cooperative driving. Due to the public trust, safety issue, or legal issue, we still want the human in the loop of the control system. So it triggered a human-machine cooperative driving. We believe that this cooperative system can combine the advantages of human driver and robot. And so that's the motivation of human-machine cooperative driving. And this is the structure of a vehicle system. I guess you must be very familiar with it. We have a different layer here. And for example, the sensor, the autonomous vehicle always has the LiDAR sensor, camera, or the GPS. These sensors can have to collect the raw data from the vehicle surroundings, such as the location of the other vehicles, where are the pedestrians and road conditions, traffic sign. And this data then goes to the perception layer, which create a detailed understanding of the environment and identify the obstacles and estimate the status. Then this information will go to the prediction layer. It used to predict the future motion of the other traffic participants, including vehicle, pedestrians, cyclists. And then the decision-making layer will make a decision based on the prediction layer. They can determine the vehicle's next step, and the motion planning and control. Motion planning will generate a safe, efficient, and comfortable path. Finally, the control layer manage the speed, steering, and braking with accurately carrying out these commands. Okay, this is called pipeline architecture of an AV system. We also notice there is another architecture called end-to-end. Okay. End-to-end means that we don't have multi-layers. The input signal just the raw data collected by the sensor. And then we directly output the control actions like the steering wheel angles or the braking torque. The benefit is very obvious because it has the ability to learn complex driving behavior from the data and optimize the entire driving pipeline jointly. Okay, so it actually is a very attractive topic in the autonomous driving. And this is the structure of human-machine cooperative driving. It's based on the pipeline architecture, where we want to input the driver's commands, preference, personalization into the different layers to help improve the performance of the driving. Okay. And this figure also shows the structure of human-machine cooperative driving. It has been clarified into 3 different layers. First one is the route planning. It's like a global route planning. The driver and system collaborate to plan a route. So it considers the factor like time saving, energy efficiency. And second one is the decision-making layer. it can be influenced if the driver changes the direction, requiring the system to replan or confirm a new destination. And at the planning and control layer, driving involves steering and speed control based on a plan. So this is done through a trajectory planning with the driver intervention, shared control, decide the final input on the vehicle. Currently, my research team focus on the bottom level, shared control and cooperative driving trajectory planning. Yeah. Before we talk about the technical details, let's have a brief introduction of the research control and cooperative driving path planning. So the definition of the shared control is how to make the human driver and automation system work together to achieve a control task. For example, changing the lane or do the U-turn. And based on the different types of steering system, it can be divided into direct shared control and indirect shared control. So if you look at these mechanical systems, you're going to find the main difference is that in indirect shared control, the driver's input does not directly transfer to the steering system. It goes to the ECU, electrical control unit first, and after calculation, after design, this signal will then goes to the vehicle's steering system. Well, in my research, we usually focus on this indirect shared control because it provides more frequency of design. Well, next one is about the human-machine interface. So, based on the modality of human-machine interface, it can be represented in visual, auditory, and haptic. So, basically, the first two types are usually used to provide some warning signals. By using the haptic interface, that will provide some vibration signals on the steering wheel, then it can actually provide useful torque feedback. And in this case, it can somehow assist the driver to understand the current driving situation. And when we talk about the controller design, it can also be clarified into reference-based and reference-free-based. So it is easy to understand. For the reference-based means that we always have a reference signal. So in the control theory, we know that sometimes we have a reference signal and we have a controller, and the controller is used to check the reference signal all the time. So in the reference-based, we always have a reference trajectory, and automation will always correct drivers or vehicles status if there's a difference between the reference trajectory and the current trajectory. So if you look at this figure, you can consider that that automation and human actually work together all the time to finish a task. When we talk about the reference-free based system, means we don't have a reference signal, and the automation works as a supervisor. Means that if you behave very well, the supervisor will not show up. But if something wrong, if you need some help, the automation will show up and provide some guidance. Okay, so you can see the difference. And in our research, we only focus on the reference-free base because we believe in this case it can reduce the human-machine conflicts. Because if someone enjoy driving, they don't want to have annoying corrections all the time, then they prefer to switch off the automation, right? So as we believe that the reference-free based approach is much more promising because we only show up, we only provide guidance if there is a need. Okay, it is related to the reference-based approaches. So if we design a reference-based approach, we need a reference trajectory. But how to design the reference trajectory? There are a series of factors we need to consider, like safety, energy, limitations, and other issues. Okay. And also, if we want human machine work together in a very well way, we need to understand the driver's status, right? If they what we're gonna do if the driver is fatigued or distracted. So we have to estimate the driver status all the time. Okay, driving risk. Yeah. So if we talk about the reference-free based, as we don't have the reference trajectory, so how should we know when we should provide assistance when the human driver need us to help them? So we have to estimate driver risk. Okay, this is a very simple way. If we find the driving risk is very high, we just need to correct the driver's behavior. If the driving risk is relatively low and we don't need to provide any warning signals and everyone is happy. So there are different approaches to estimate the driving risk, time-based, like TTC, very traditional one, kinematic-based, potential field-based, or probability-based. And for the last three approaches, they always need to rely on the trajectory prediction. So in the academic, we have several different approaches, like physical-based approaches, maneuveral-based, and interactive action-aware-based. So interaction-aware-based, based on this name, you can guess how it works, right? Or can guess the principle. It means that you consider the interaction among the different traffic participants and then provide a deterministic or probabilistic prediction results. It is quite, I think it is a very promising approach because it is more realistic compared to the other two approaches. Last one is about the testing environment. So as I don't have the real test vehicles, I only focus on the small robot and the driving simulators. So that is what we have right now. Yeah, this page introduces some commonly used path planning algorithms in the literature. So geometric based, optimization based, graph based, and sampling based. Each of them has its own advantages and disadvantages. So I actually focus on the sampling based. I think the main reason is because it has a very high computational efficiency. So later I will show you a demo. Okay, so let me just have a look. Oh yeah, first step is to establish a virtual traffic environment for testing. Okay. Oh, doesn't work. So we actually, the color is a very commonly used platform for you to do the testing. They already have mature testing environment, but we want to design an environment by ourselves. So we established a 2 kilometer traffic testing environment centered around polio. My previous affiliation, we collect the real traffic data in Hong Kong to ensure that the surrounding vehicles and the road conditions within the testing environment can accurately reflect the trajectory condition in Hong Kong. We also ask the Hong Kong drivers to play with our driving simulator and give our some cognitive feedback. Okay. Yeah, as we want, yeah, we need to understand the driver's behavior so we can better improve their driving skill or better help them with the driving. So on this page, we actually conduct some work. We identify the driver's behavior as abnormal and normal behavior. For example, if in the driving you command your hair or you're talking on the cell phone, we will clarify it as an abnormal behavior. In this case, the driving risk level will be increased, right? And also we estimate the driver's attention during the driving. So I think it is quite interesting topic. As shown on the screen, we actually use the Gaussian distribution-based attention map. The red region represent the main focus area, while the surrounding green and blue regions represent uncertainty and spread of the driver's attention. So the driver's attention actually you can find is continuously shift, sometimes towards the upper right side of the road, sometimes towards buildings or other objects. So based on this map, based on this estimation, we can identify if the driver is focusing on the driving or if he or she is fatigued or distracted. Okay, previous page focus on the driver, focus on the in-cabin information, and this page focus on the out car information. So we want to do the prediction. We want to use the historical data to predict the future motions of the other vehicles, cyclists, pedestrians. So here, we actually consider multi-interaction, car, pedestrian, car cyclist, and cyclist pedestrian, and then provide a probabilistic results. So we believe that this probabilistic result represent more realistic information compared to the deterministic results. So I just use this figure to show how what does it mean. So if you find this line, it actually shows the future motion of the vehicle one, and you find that this is a dark yellow. So the dark yellow actually represent with a high possibility. Here, with a high possibility, this vehicle one will turn left, but we still have this two line. Okay, so means that with a small possibility, this vehicle one will do the U-turn. Okay, we use this probabilistic information to represent our prediction results, because we think, yeah, it is more realistic. And after we get the prediction results, we can do the collision probability. Okay, based on the probabilistic information, we calculate the collision probability. We also know the driver's behavior, normal, distracted, or fatigue, or focusing. We also can estimate or monitor the vehicle status. And we can also find that if the drivers break the traffic rule or violate the traffic rule, if the driver is speeding or not. So based on this information, we use the Fuzzy inference system to generate driving risk level. Okay, so if you see this figure, we have this several bar. The different bar represent each like important factor, like the collision risk, driving instability, and also totally we will give overall driving risk level. Yeah. So the green means that means a low risk. If it goes to this part, you're gonna see that it will turns to red, and it means that at this moment we have a high driving risk. So what should we do if we estimate a high driving risk? We're going to generate a path. Okay, we're going to generate a path for the vehicle to follow. Okay? Because due to the Hong Kong policy, we cannot directly control the vehicle, but we can provide some guidance. So in this case, we try to design a path. And theoretically, if the vehicle follow that path, we can guarantee there's no collisions in the near future. And as I mentioned, we use the RRT. We designed a human motion RRT algorithms because it can quickly draw a tree and cut the unuseful branches and quickly find the feasible path. So this is some simulation results. And that is how we grow a tree and cut the branches, and then finally find the physical tree. And to speed up the calculation, we actually did at every sampling time, we didn't regrow the tree. We actually used the previous tree and cut some useful branches. So in this way, it means that we can save a lot of computation time. Sorry, forgot to mention. And also we consider the driver's driving skill. So if we find that the driver is very aggressive, then we actually provide a bigger safe area. We provide a bigger safe area. And in this case means that we're gonna have a smaller tree grow area. Means that for the aggressive driver, we actually provide a much more safer path for them to follow. Here are some demos. Okay, doesn't work. Okay. Well, exchange. Okay, so actually this green line is the path we generated. It's shown on the wind shift. It not just occurred continuously. When we have a high driving risk, this green line will show up and let the vehicle or the driver to follow. That works. Okay. So it means that we think we're gonna have a real collision, and in this case, we just suddenly show a lane changing path, and if the vehicle follow this lane changing path, we will not have a collision. Okay. We also worked together with this Hangpo transportation company. We equipped their bus with the lidar and the radar, collect the data and run our algorithms to verify the effectiveness of our this path planning algorithm system. We also monitor their drivers in the driving, because they would like us to provide some report to identify the driver's behavior in the driving. Okay. Okay, this one is about the shared control. As I mentioned, we are not allowed to directly control the vehicle, but we still do some theoretical development. This page shows two work. One is my very old work when I was a postdoc in Singapore. And another work is conducted by my PhD student. Based on my research work, he improved it and provide a new novel shared control system. So if you look at this figure, it shows how the human driver and automation system work together to control a vehicle. You see that the drivers input the steering wheel angle and braking torque into the vehicle system. Also, the automation system provide delta A and TA together, and then put it together with the human driver's input and goes to the vehicle system. But as I mentioned, we don't want to make the drivers annoying, because we don't want to continuously correct their actions. We only want to provide assistance if needed. So when I designed this MPC controller, I actually designed objective as minimizing the UA. So it means that we want to minimize the value of the automation system, and we design a series of constraints. So it means that if you understand the MPC framework, if the constraints are not violated when you solve this MPC problem, the output will be 0, right? Because we want to minimize the UA. So the UA will become 0, and means that the automation system will not provide any assistance. But if any of the constraints is violated, we're going to have a value of UA, and together with the driver's input, the U will go to the vehicle. Okay, that's how we design to reduce the human-machine conflicts. Okay, so here are some demos. We identify the driver states, and we find that it's distracted. And then we actually switch the authority between the human and automation. And in this case, it shows that in the driving, the automation system can identify the occurrence of some abnormal behavior. Then we provide some corrective steering signal, and together with the driver's steering signal, the signal goes to the vehicle and then rotate the vehicle, the front wheel, avoid some collisions. Okay. And in my PhD student's work, based on my research work, he further considered the interaction between our vehicle and the other vehicles. So in my previous work, I only considered the interaction between myself and the vehicles I sit inside. In his work, besides that, he also considered the interaction between us, our vehicle, and the other surrounding vehicles. So here are some simulation results. The left side shows the shared control. It considered a very dangerous case. So I just run it. Now let's look at the manual driving. So you can find that in two cases, we have the similar driving scenarios. We have a targeted vehicle. We want to change the lane to the adjacent lane, but we find that this vehicle doesn't give way to us. Okay, so it's kind of very challenging thing. It requires quick reaction. It requires the accurate judgment from the driver. So we find that, okay, maybe due to limited driving skills, the human drivers manually drive this vehicle leads to a collisions. But with this shared control, we can avoid collisions and then force our vehicle back to the current lane and avoid the collisions. Okay, then we can go to the final topic. It's about autonomous driving. In this topic, we don't have the human driver. As I mentioned, we have a pipeline architecture, and we have different layers. Decision-making layer, we believe it is quite important. It can determine the next step of the vehicles. So we had a survey paper talking about the current existing methods related to the behavior decision. We find that it can be classified into different approaches, like the rule-based, data-driven based, or game theory. Okay, whatever. So we focus on the data-driven based approaches. we find that there are a series of reinforcement learning algorithms in the literature. And we are focusing on the human-guided reinforcement learning algorithm. Just as this name shows, in this reinforcement learning algorithms, we want to input the driver's motor driving skill and to help improve the training process and help to speed up the training process. So that's the idea and motivation of our algorithms and approaches. So I will introduce 3 research work conducted by my postdoc and PhD students. So in this work, our goal is to learn how human driver make decisions and train our algorithms to do the same. So there is an example. Okay, here is an example shows how the human make the decision in the driving. So you can find out we have three different scenarios. We drive this car. We have a car try to cut in. We drive this car. We have a car may not want to cut in, but drive very close to you, so it's still very risky. And in this case, we have our car, but we have a motorcycle, and this motorcycle try to cut in. Okay, so when we encounter these 3 cases, we may categorize these cases as imminent collision threat. So usually, we're gonna give way and let them change the lane. Okay, that's what we're gonna do. But for the data-driven method, even small changes in the scenario can lead to like different training results. To achieve the same decision of slowing down and giving way, the learning-based approaches require long training times. So in this case, we find it challenging. To solve this problem, we use the WIE to let our AI agent to effectively understand and respond to complex driving scenario, just like a human driver. So that's how we designed. And these are some results. We find that compared with the other approaches, in a continuous lane changing scenario, we have no collisions. But the other vehicle approaches always has a collision rate, and some has just light, maybe small collision times, but they may have a longer like frequency, a longer lane changing time. So it means that, okay, our algorithms are much more safer because we don't have collision and we can like achieve a lane change very quickly. So here is the video. It shows how we like continuously change the lane here. And the second work was conducted by my PhD student. It focused on improving the safety and efficiency of reinforcement learning navigation. The key idea is inspired by human psychology. When humans explore an unknown environment, our decisions are often influenced by 2 factors, curiosity and fear. Okay, so we create this word. It means fear plus curiosity. So the curiosity encourage exploration, but fear help us avoid potential dangers. So based on this observation, we propose this curiosity guide reinforcement learning framework. It can like explicitly models both curiosity and fear within the learning process. The curiosity model can encourage the agent to explore unfamiliar situations, while the fear model use a learned world model to estimate potential risk and use behavior. So these 2 components can integrate it into the reinforcement learning framework to balance the exploration and safety. It also figure shows that we achieve higher rewards and success rate while maintaining a lower collision rate than existing approaches. So here is a video. Okay. Yeah, this is our approaches. Okay, the left top one. Okay. Then we go to the last task. This task extend the idea of human in the loop reinforcement learning. Existing approaches assume that the human guidance is always beneficial and should always be incorporated during the training, but this assumption is not always true. So the key novelty of this work is the introduction of a trust calibrate mechanism. So instead of blindly following the human intervention, the agent continuously evaluate the quality of human guidance and calculate a belief value. So when the human guidance is beneficial, we incorporate it into the training process. When the agent becomes more capable and the human guidance is no longer helpful, the intervention is automatically masked. So in this way, we combine advantages of human knowledge in the earlier training stage, where the learning capability of reinforcement learning in the later, not this one, this one. In the later stage. I think I'm running out of time, so just last slide. I just want to thank, I acknowledge my researcher team. Many of the projects I present today was primarily carried out by my students and postdocs. So I'm very grateful for their hard work and contributions. Thank you.
All right. Thank you. Thank you very much, Dr. Huang's excellent presentations. So basically, we have really seen lots of interesting and informative videos regarding those proposed methodologies. So Dr. Huang's give us a talk regarding the path planning, trajectory design, and multi-UAV collaboration. And in the second half of his talk, her talk, so she detailedly described the human-machine cooperative driving and fully autonomous driving for ground vehicles. Yeah, so those the videos and demos are quite informative for all of us. So now I think it's the question and answer section time. So are there any questions from our audience? All right, so Fang Yi.
Yeah, hi. Thanks, Dr. Wang, for taking your time to share with us all these interesting works, particularly in such a busy period of time at the end of a semester. I just have a very high-level question because nowadays the visual language action models are evolving in a very fast pace. And have you seen any, like, say, changes because of this kind of VLA advances in the areas you are focusing on, kind of, particularly for the, say, human machine cooperative driving? Because from my understanding, probably the visual language action model does provide some kind of like new interfaces between the communication, like say, for the communication between humans and machines, like a automated vehicle.
Yeah. I actually agree with your comments. In the fourth sim, I have another research direction. It's about the indoor robot. I haven't talked about it yet, but actually we already apply this voice interaction, like the language issues in the indoor robot. We believe that it can improve the mutual understanding between the human and the robot. So in that case, we consider that language as an input, and it can help guide the robot in the navigation and control. So we have a demo, we have a case that the robot just go drive, go follow their desired path from the one position to the destination. But during this procedure, we have pedestrians, they may just follow the robot, but somehow we find that okay, the robot is has a very low speed and we want to overtake or somehow, so we just speak with this robot, say that please give way to me or please let me go, and then the robot just take actions and give way to the pedestrian, so the pedestrian can overtake the robot. So in this case, we actually consider the language interaction to mutual understand each other.
Yeah, great. Thanks for sharing this.
Thank you.
All right, thank you. So any more questions from our other audience? Yeah, so in today's talk, I think Dr. Huang talked a lot regarding the embodied robots, the topics. Yeah, so I believe all of our audience should be having lots of questions. Yeah. So next one, the Sharon. Yeah.
You mute yourself.
Sharon, you're muted.
Can you hear me now?
Yeah.
Yeah.
Yeah. So thank you, Professor Shaw, to share this informations and your research with us. And I'm just curious about the research that you had done, especially in the case of UAV vehicles, which is used for delivering purpose, that you are trying to find the shortest path and considering charging progress as well. So I would like to ask about the path planning. Like, how do you define that shortest path in your research? Like, is it like the shortest distance, or is that the shortest time that you're considering, or is that the minimum energy that you consumed? So what is your framework of defining the shortest path in your research one?
Yeah, it should be like multi-objective. The first, the high priority is that we need to deliver the parcel to the customer before a given time. Yes, right. Otherwise, the customer will complain.
Okay.
And yeah, besides this high priority, we also need to consider the energy consumption and also the short distance as well. So it's actually a multi-objective optimization problem.
Oh, okay. Yeah. Thank you.
Okay.
And have you considered is it needs to be like an trade-off, kind of finding a balanced trade-off between the longer path to reach a charging station, or is like
Yeah,
at the risk of
yes.
running out the battery? Oh, okay, got it.
Yeah, because we design some weighting factor, so we have to
Okay.
use this factor to do some balance.
Oh, okay. Yeah. Thank you.
Thank you.
Any more questions from our audience, from the students? Shoy?
Hello, can you hear me?
Yes.
Hello, Dr. Chao. I had a question. In your UAV monitoring system for the vehicles, so what do you think that will be the best suited option? Is it a decentralized option or a centralized one?
It's a decentralized approaches, so that can be one of our contributions. Because the motions of the UAV only rely on the motions of the surrounding UAV. So it's a decentralized approaches. Means that these approaches can be easily extended to a large group of UAVs.
Okay, and when you just monitor the vehicles with the UAVs, in the practical scenario, inside a flying bird could come, or there should be rain. Does these factors will affect your visualization of the tracking vehicles?
No, it's not a visualization, it's a communication channel.
Communication, yeah,
So yeah. We believe that this line of sight constraints can have a negative impact on the communication constraints.
Okay. Thanks. Thank you.
Thank you.
All right. So thank you, Dr. Huang. So I have one question regarding your experiment platform. Yeah. So could you please give us more detail regarding those both of hardware information and software information for that the platform regarding the human machine cooperative planning, those this kind of platform that.
Human machine cooperative driving. Yeah. Okay. We have a driving simulator. We use the branch called Next Level. I think it's a very famous racing branch. Yeah, and for the steering wheel and panel, we need to we use the Logitech branch. It can easily for you to encode your control signal into the computer. And yes, and we also have a Songling robot. It can be considered as a vehicle. So when we design this cooperative driving, one way is that we only use the driving simulator. We establish a virtual testing environment. We have a virtual car in the virtual environment. Then we let the human driver sit in the driving simulator, and then we run our algorithms at the same time and can be like stimulated as the shared control. Or we can have like driving simulator and a robot vehicle. So the robot vehicle can be considered as a vehicle, and we
Yeah.
run it in the indoor laboratory.
Mm.
So we steering the steering wheel and drive the vehicle. The small robot vehicle will then follow our commands.
Mm. All right.
Yeah.
So, do you know what's the estimated cost for this kind of the platform?
Oh,
I know it should
Driver
be.
simulator is quite cheap.
Um,
I think let me think. Okay. Maybe 200 to 300 Australian dollar is enough to set up a driving simulator platform.
to 200.
No,
200,000.
2,000. Sorry, my mistake. 2,000 to 3,000 Australian
Okay.
dollars. Yes.
Yes. Okay.
And for the robot vehicle, it is quite expensive if you want to equip it with some lidars or yeah, that will be expensive.
Okay. So in terms of software, it's all open source. We can all we need to buy for those software.
You can buy, but I think due to my limited budget, my students just like establish and explore by themselves. They don't buy any software. Yeah, they don't buy. And for the color, you see the virtual environment we established by ourselves, but you can directly use the color. They have so many frame testing environment. You don't need to buy anything.
Okay, so maybe in the future we need to get more guidance from you regarding this, setting up those kind of platform. Yeah, this is quite useful for the PhD students to do some of the corresponding researches in this area.
I understand. Yeah.
Okay. Yeah. No problem. So thank you very much. So any other comments or queries or questions from our audience? Otherwise, we may finish for today's talk. I know now it's quite late. Yeah. All right. So if there's no questions, so let's express our sincere thanks again for Dr. Chao Huang's talk for our first women engineering event for IEEE VTS chapter. So in the future, if we we would like to warmly welcome and host Dr. Huang coming to Perth to give us the face-to-face talk. In future, if sometime if available, definitely we are very happy to host you, in person.
Thank you.
Yeah. All right. So thank you very much again for delivering the talk for us, and enjoy this the weekend. Thank you. Thank you very much. Thank you.
Bye bye.
Yeah. Cheers. Bye.